Hello viewers, welcome back to this channel. So in this video we are going to be proceeding with the second video about thermochemistry. So in this video we are going to be covering specifically bond energy and energy level diagrams according to Hess's law. Now starting or commencing with bond energy terms, we are going to be looking at specific reactions whereby we are going to be calculating enthalpies of reactions using bond energies that are going to be specified in each and every question that you are going to be tackling. So starting with bond energy terms, as we had already covered the first part, which was part A in the previous video. So here we are going to be saying that during a chemical reaction, energy is supplied, and energy is already supplied so as to break the bonds that are involved in the reactants. But whenever we are forming products, always energy is liberated. So the key takeaway of this statement or the paragraph is that for reactants to undergo specific chemical reaction, they require energy, or such type of a reaction must be endothermic. And for products to be formed, bond formation causes release of energy. So that's why we are saying that energy is liberated so as to form bonds that are involved in the products. So going to bond strength. Now looked at the factors that affect bond strength in different reactants and products in the previous video. So here we are going to be saying that bond strength are commonly described by their bond dissociation energy, which is the energy required to break one mole of a bond of a particular type. Now we defined bond dissociation energy in the previous video, and we say that is the energy required to break one bond which is present in a diatomic molecule into its constituent gaseous atoms. So you should be knowing the definition of bond dissociation energy. You should also be knowing the definition of bond energy. So you're going to be saying that bond energy is going to be the average energy which is required to break one mole of a particular bond, for example, a bond between a diatomic molecule into its constituent gaseous atoms. So here we are going to be proceeding by saying that bond energies can be utilized in estimating enthalpies of reactions. And with that, we are going to say that the enthalpy change in the reaction is going to be the summation of the energies required to break the bonds between the reactants, and also that is liberated when the bonds of the products are being formed. So you are going to be using a general formula which is equal to enthalpy of reaction to be specified by bonds broken. Now with bonds broken, we are meaning the energy that is required by reactants to undergo chemical reaction. And then minus, it must be minus, this is not a plus sign, so it must be minus summation of the energies from the bonds that are being formed. In other words, it's going to be, the formula can be summarized like down here. Enthalpy of reaction is going to be equal to summation of bond energy of the reactants less summation of all the bond energy of the products. So you should always know that reactants, when they are for them to undergo chemical reaction, energy must be positive, and for products, for them to undergo chemical reaction, they give out energy. So that's why there is a negative here, but the coefficient of this one is positive, because reactants bond energy is going to be positive and products bond energy is going to be negative. So you are not allowed to put any sign within the brackets as you are getting your summation. So you're going to note down that energy terms associated with bond breaking have positive signs, whereas the formation of bond releases energy. So the energy or the energy terms associated with bond making or bond formation are going to carry negative sign, and therefore our enthalpy of reaction is going to be deducted by this formula. Summation of the bond energy of reactants less summation of the bond energy of the products. So starting with the applications or the use of bond energies in chemistry as applied to advanced level, we are going to be looking at the bond energies or the average bond energies that are involved in specific bonds between specific diatomic molecules or same atomic molecules. So the hydrogen to hydrogen bond contains a bond energy of 436. I said that here when you're using that formula, you don't require any sign, either positive or negative, on the energy terms, and energy is measured, or bond energy is measured in kilojoules per mole. And you say that reactants require energy, therefore they carry a positive sign, and products to be formed, they release energy, and therefore they carry a negative sign. So we're going to be saying that below some of the bond energies of the terms that are involved in our calculations. So the hydrogen to hydrogen bond is going to contain an energy of 436 kilojoules per mole, whereas the carbon to hydrogen bond is going to contain an energy of 412 kilojoules per mole, and the carbon to carbon bond, or the carbon to carbon double bond, is going to contain an energy of 615 kilojoules per mole. And similarly, the carbon to carbon single bond is going to contain an energy of 348 kilojoules per mole. Now these energies are standard, and always in your papers they will be specified, but in case of you having any revision question and it requires you to refer back to this table, make sure that you highlight it so that you can easily come back and you look at the energy terms of the each and every bond that is present in the question. So you're going to be calculating the enthalpy change for the reaction that is involved when ethene is hydrogenated so that you can form ethane. So the solution here, we are first going to talk about the highlight. So the highlight here, we are going to be saying that the idea is that when you're breaking bonds of the gaseous reactants to give individual atoms, and then we assemble them into gaseous products by formation of new bonds. So formation of products is going to release energy, and therefore we expect bond energies of products to carry negative signs. And also for reactants, for them to undergo a chemical reaction, bonds must be broken. So therefore energy is required so that you can form atoms that can later undergo the chemical reaction to give us products. Now let's look at how the calculations can be implemented. Now when dealing with bond energy reactions, the first thing that you have to do is that you have to get the equation that you have been given, or all your reactants and the products, all the bonds in that structure must be distributed and well properly elaborated for the examiner to see them properly. So we separated the thing into its respective structure, and the reason why we do that is because we want to see how many bonds, how many carbon to carbon bonds and how many carbon to hydrogen bonds are present. Also hydrogen, we make it in terms of a structure to see the number of bonds present, and same applies to our product, which was the alkane. So the enthalpy of reaction is going to be equal to, according to our formula, summation of bond energy of the reactants. And bond energy of the reactants, we are going to get it by getting the number of bonds times the multiplied by the energy value it contains. So if you look at carbon to hydrogen bond on the reactant side, because this bracket, or the first bracket, is showing summation of energy terms of the bond energies of the reactants. So here, if you look at carbon to carbon double bond, we say that it's 1. We have only one carbon to carbon double bond. So that's why you're seeing its energy term without a sign, being 615 as we specified in the table. But here you are seeing 4 multiplying 412. Now remember that 412 is the bond energy for carbon to hydrogen bond. But if you look in this structure of alkene or ethene, we are having 4 carbon to hydrogen double bonds. So that's why we multiplied 4 by the energy term of the carbon to hydrogen bond. And then the other term that we have in the reactants is the hydrogen to hydrogen bond, which was given as 436 kilojoules per mole. And then we less summation of our energy or bond energies, or summation of all total bond energies of our product. And if you look at our product, we have only one carbon to carbon single bond. That's why you're having here 348, and you're having 6/6 carbon to hydrogen single bonds, and that's why you're having 6 multiplying the energy term or energy value for a single carbon to hydrogen bond. So this is going to be summation of the bond energies of the products, and this is going to be summation of the bond energies of the reactants. Now once you put everything in the calculator, your final answer must carry a sign, which is going to be negative 121 kilojoules per mole. And this means that 121 kilojoules per mole of heat were released once we hydrogenate ethene to get ethane. Now you're going to note that the calculated and the experimentally determined values are not going to be the same. The difference arises from the use of average mean of bond energies. The values that we are using here, they are just averagely determined bond energy values, just like we determined them in the previous video. So you're going to be looking at number 2, and number 2 you're going to be saying that some of the bond energies, which is represented by Be, are given below. So the carbon to hydrogen is 412, carbon to oxygen is 803, and then oxygen to hydrogen is going to be 463. Oxygen to oxygen bond is going to be 496, and then carbon to oxygen is 326. Carbon to carbon triple bond is going to be 813, and carbon to carbon single bond is going to be 346. Hydrogen to hydrogen bond is going to be 436. Now there's always a mistake in sketching or writing the work, but notice that each and every bond that has been given, always you are going to use almost all 99 of the bond energies that have been given in the question. So here they are asking us, or they are prompting us to use the bond energies given above, so that we can calculate Roman number 1 for the standard enthalpy of combustion of methanol. The solution for that is that you first need to write the equation. Now here the equation, I didn't make it in terms of a structure, because for me, I'm somehow now skilled. I can recognize how many bonds are present. But for your case, you must first explain this equation that has been given in terms of this example that I gave here, so that you can quickly see or easily see the number of carbon to hydrogen bonds and the varieties of the bonds that you are having in both the reactants and the products. So the balanced equation for burning the combustion of methanol or burning methanol in excess oxygen is going to give us carbon dioxide and water. So the first thing you have to do is to ensure that each and every reactant and product, they're in correct or normal states, because that's a very important thing in thermochemistry. And the other thing to ensure is to make sure that your equation is properly balanced. So number of carbon atoms, number of hydrogen atoms, and number of oxygen atoms on the left hand side must be the same as those ones on the right hand side. And after making sure that your equation is balanced, you try to make it in terms of a structure. You draw it in terms of a structure like we did up here. Otherwise, if you can easily see them, but I feel like you'll be making mistakes. So you draw them in terms of a structure to see how many bonds you are having. Draw your reactant in form of a structure, oxygen in form of a structure, carbon dioxide in form of its structure, and also water in form of structure, so that you can see the bonds or types of bonds that exist in various reactants and the products. So you're going to quote our formula that enthalpy of reaction is given by summation of the bond energies of the reactants, you less summation of the bond energies of your products. So if you look at our reactants, you have methanol. Now in methanol, we are having 3 carbon to hydrogen bonds. So that's why we are going to get 3. We multiply it with the carbon to hydrogen bond energy that has been given in the table. And then we also have 1 carbon to oxygen bond. We also have an oxygen to hydrogen bond within methanol. So all these 3 bonds are coming from methanol alone. And then the oxygen gives us the oxygen to oxygen double bond. We give it its coefficient since it's already present in the balanced equation. And then the reactants are going to give us summation of bonds that are present in carbon dioxide. They are going to be 2. Remember that carbon dioxide is discrete. When you're sketching it, it's in that form. So we form 2 carbon to oxygen bonds, this one and this one. So that's why we put here 2 multiplied by the carbon to oxygen bond, and then plus the summation of the bonds that are present in water. And the bonds that are present in water is the same as oxygen to hydrogen. It's the oxygen to hydrogen bond. And since there are 2, so one of the hydrogen was not supposed to be there. And since there are 2, we put here 2 to show that we are having enough oxygen to hydrogen bonds present. Now on substituting of the required values with the bond energies or bonds that you have represented above, you're going to have 3 into 412, then plus 326, then plus 463, and then plus 3 over 2 into 496, then minus those of the products, which is 2 into 803. Now you may ask yourself, where is this 2 coming from? Remember that this 2 is the coefficient that is present on water. And then this 2 is because you're having 2 oxygen to hydrogen bonds in water. So 2 oxygen to hydrogen bonds multiplying the energy, the bond energy of 1 oxygen to hydrogen bond, so that we can get the total bond energy in water. The 2 are multiplying it here with this energy because it was present as a coefficient in our balanced equation. So putting everything in the calculator, the product side or the reactant side is going to give you 2,769 kilojoules per mole, and the reactant side or the product side is going to give you 3,458 kilojoules per mole, and the difference between the two is going to give us the energy we require. And the energy, most of the time is going to be negative, to show you that product formation or formation of bonds always releases energy, so that's why it's always negative. So it's going to be negative 689 kilojoules per mole. And Roman number 2, we are going to be saying that the enthalpy of hydrogenation of ethane, is not feasible, is feasible. Okay, the Roman number 2, they wanted you to comment about this answer. So the comment is, you say that hydrogenation of ethane is going to be feasible. Reason being, the enthalpy of reaction that you have got is negative, or it is exothermic. Now you're given here a task, don't mind about this. Okay, maybe there was a typing error. So in this task, you are going to write this question down and then you try it out on your own to see whether you are going to come up with the required answer. I think the answer for this is going to be up here. This answer I think was just misplaced. So make sure that you try out this question, try to discuss it with your friends, take it to your teacher for analysis, and see whether you have got it right. So pause the video and take the question. So the taking of the questions, the question proceeds from here to here. There are going to be 3 numbers, I think maximum, to test out your understanding, because all these ones require practice for you to master them. You can never be good at thermochemistry without practice. So that's why I gave you enough numbers for you to do out so that you can be confident when you're answering your papers. So try out the numbers, see your teacher in case you find any problem, or review the way I explained the things so that you can easily get these answers that I suggested above. In case you're having any challenge, try to reach me out as soon as possible. So pause the video and take the questions. Now these are the questions that are going to be summarizing calculations that are involving bond energy. So I pause the video, take the questions, try them out, reach your teacher out. In case you can't access your teacher, try to reach me out. I know I'm busy, but at least I may reply later after some hours. So try taking the questions, try to discuss them with your friends, make sure that you are more into discussion so that you can easily get these concepts stick in your short memory or short-term memory, so that you can easily execute them and you can easily grasp them in your long-term memory. But make discussions your friend if you want to be good at chemistry. Now another concept that you're going to be handling in this video, which is the last part, is going to be Born-Harber cycles and also energy level diagrams. Now energy level diagrams are the ones that are going to be helping us to determine lattice energy. So a brief introduction about the Born-Haber cycle is that this is the cycle that is going to break down formation of 1 mole of anionic compound or anionic solid or anionic electrolyte into a series of individual steps. Now the elements that are present in their normal or standard states are first converted into gaseous atoms. Then from gaseous atoms, we convert them to gaseous ions. And then from gaseous ions, we pack them into a crystal lattice. And if you remember the concepts of thermochemistry properly, we say that lattice energy is that energy that is released when 1 mole of an ion crystal lattice is formed from its constituent gaseous ions. So before we get those gaseous ions, we first get the elements in their standard states, we convert them to atoms, from atoms we convert them to ions. It's those gaseous ions that react together to give us what we call lattice energy. Now we are going to be involving different symbols when you are drawing those diagrams, and we are having here a key so that you don't get lost in case we start them. So the symbol, this is going to denote the standard enthalpy. Delta H subscript F is going to denote the standard enthalpy of formation of any specific compound, which is always going to be prescribed on the diagram. And then IE is going to represent the ionization energy of the metal that is being dealt with. And then EA is going to represent the electron affinity of the non-metal that we are dealing with. So you should note that ionization energy is only going to apply for metals, and EA or electron affinity is going only to apply for non-metals. Now delta HS is going to be, or is going to represent, enthalpy of sublimation of a specific metal. Now in the previous video, we said that enthalpy of sublimation is only specific and only specific to solid elements that exist in solid state. Others are going to be denoted by enthalpy of atomization. And then BDE is going to represent bond dissociation energy of the non-metal, because it's only non-metals that possess such type of an energy. So BDE is going to be the bond dissociation energy of the non-metal. Then delta H of the lattice is going to represent the lattice energy of a specific compound. Now looking at this, we are going to have the energy changes that take place in the Born-Haber cycle, and we define each of them. We try to review each of them in details before we start our energy level diagrams or our Born-Haber cycles. So we are going to start with the atomization energy of a gas. Now remember that most of the gases we are having here in chemistry, they are diatomic. Chlorine is diatomic, nitrogen is diatomic, hydrogen is diatomic. So what we do is that we atomize them so that we can get gaseous atoms, just like prescribed above, from gaseous atoms to gaseous ions. So the energy required to convert an element or a molecule into an atom is called atomization energy. So we're going to say that atomization energy is going to be the energy required to form 1 mole of a gaseous atom. And we say that in the previous video that atomization energy is half the bond dissociation energy, and I explained this one very well. So let's proceed to the next details. The next energy term that you're going to be looking at is going to be the ionization of a metal. Now in this ionization of the metal, this is the same as ionization energy, and you're going to define it just like we define it in periodicity, that this is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms to form 1 mole of positively charged gaseous metal ion. And to represent that is going to be, you find a gaseous atom. When we remove an electron from it, energy required to remove an electron from it is going to give us ionization energy. So proceeding to electron affinity is going to be the energy given out when 1 mole of electron is added to 1 mole of a gaseous non-metal atom, so that we can form a 1 mole of a negatively charged non-metal ion. So whenever you're having an atom, a gaseous atom, and you add an electron to it, first of all it becomes negatively charged, but also addition of electrons is going to release energy. So the energy released is what we call electron affinity. and we say that electron affinity only applies for non-metals, and ionization energy only applies for metals. So you're saying that note here that the first electron affinity is going to be negative, but the second electron affinity is always positive. Reason being, after adding an electron, work must be done. And this work which is being done requires input of energy or absorption of energy from the surrounding or the environment, so that we can add the second electron against the repulsive force exerted by the first electron. Now we looked at this explanation more in details under periodicity. So here I'm just highlighting or reminding you about such an explanation. So work must be put, but this work which must be put is in terms of absorption of energy. Now when you absorb energy in putting an electron, that means that the energy which would have been evolved is instead absorbed, and therefore enthalpy of reaction or second electron affinity is going to be positive, because it shows that energy is being absorbed to add an electron to an already negatively charged gaseous ion. So that's why the first electron affinity is negative. The first electron affinity is negative simply because an electron is being added to a neutral atom. But for the second electron affinity, an electron is being added to an already negatively charged ion. So the second electron that is being added is going to experience more repulsion than the attraction from the nucleus. And therefore, we must put in some work, or we must absorb some energy to add an electron such a negatively charged gaseous ion. So with that, we shall conclude electron affinity together with ionization energy. So we're going to proceed to the main important energy, which is Lattice energy. Lattice energy is going to be the enthalpy change. That is going to occur when 1 mole of a crystal lattice is formed from or broken into its constituent gaseous ions. Now we are saying that it's going to be the enthalpy change because this definition is both for formation and also for breaking. But lattice energy can be defined in two ways. You can't bring this definition in an exam. So you either define it in terms of formation, or you define it in terms of bond breaking. So in terms of bond formation, remember that we said that bond formation causes release of energy. So you'll be saying that lattice energy is going to be the energy released when 1 mole of a crystal lattice is formed from its constituent gaseous ions. So that's the full elaborative definition of lattice energy. But if you want to define it in terms of bond breaking, then you have to use energy required to break 1 mole of a crystal lattice into its constituent gaseous ions. So that's the definition of lattice energy. You can either define it in terms of formation. With formation, energy is going to be released. With bond breaking, energy is going to be required. And therefore, there are two definitions of lattice energy. So we are going to note here that when the crystal lattice is being formed from the constituent gaseous ions, energy is going to be given out. And when the crystal lattice is being broken into its constituent gaseous ions, energy is going to be required. Now this one, the first one, we are going to be looking at it in enthalpy of solution. So you're going to find that often when you're dealing with enthalpy of solution together with lattice energy, after calculating for the value of lattice energy, we are going to make it positive, because in solution we split the ionic lattice into its constituent ions. So that's why when you're dealing with enthalpy of solution, always make the lattice energy positive. But when you're dealing with energy level diagram or energy level diagrams and Born-Harber cycles, lattice energy must always be negative, because for those ones they involve bond formation. Now demonstrating that, we are going to be looking at the following example. Now in this example, we are being provided with the standard enthalpy changes for some reactions that are given below. Now this is going to be called atomization of calcium. And atomization of 1 mole of calcium atom, or the atomization energy of calcium, is positive 193. It's positive because atomization is energy required, or atomization of any element requires energy. Now this is going to be atomization of fluorine. It's from a molecule to a fluorine atom. Now here, someone can say this one you can either call it atomization or you can call it sublimation. But sublimation is only specific to solid, and this one qualifies for it, enthalpy of sublimation. Or you can simply say enthalpy of atomization of calcium. So this is going to be atomization of fluorine atom, or fluorine element, because it's from a molecule of fluorine to an atom. And since it also requires energy, it's going to be positive 79 kilojoules per mole. And then, when you're adding an electron to a gaseous atom, we call that energy electron affinity. Electron affinity, first electron affinity is always positive, or is always negative. So that's why you're having negative 348 kilojoules per mole. And then, reaction between the standard elements is going to give us what we call enthalpy of reaction, or overall enthalpy of reaction of between two elements, and it's going to be negative 1214 kilojoules per mole. Now, ionization of calcium atom is what we call, or removal of an electron from a gaseous atom of calcium is what we are going to be calling ionization energy of calcium, and here it's going to be positive 590 kilojoules per mole. Removal of the second electron from an already positively charged gaseous ion of calcium is what we are going to be calling second ionization energy of calcium. So the questions are going to prompt us to do the following. So first, we are going to construct a Born-Haber cycle for the information given above of calcium fluoride. And next, we are going to use our cycle we have constructed to calculate for the latest energy of calcium fluoride, as it was not given among the energy values that were stated up here. So let's look at the solution. So the Born-Haber cycle is going to be in the following shape. So first of all, we write a well-balanced equation. Now, assuming that all these ones were not present, we first write a well-balanced equation of calcium reacting with fluorine to give us calcium fluoride. Now, after ensuring that every element, every reactant and product is present in its normal and standard state, we make sure that it's well balanced. After ensuring that it's well balanced, we write the enthalpy formation of calcium fluoride, which was given as negative 1214 kilojoules per mole. Now we start undergoing the different energy changes that are involved for calcium. So for calcium, we are told that we first atomize it. So we convert it from a solid to a gaseous atom. And this can be called sublimation energy of calcium, or can easily be called atomization energy of calcium. Atomization works on both solids and gases, but sublimation is only strictly on solids. So after atomizing calcium, we remove an electron from it, or it undergoes what we call the first ionization energy, which was given as positive 590 kilojoules per mole. And then it undergoes the second ionization energy to give us the calcium ion, which was given as positive 1150 kilojoules per mole. Then we also start on fluorine. So fluorine, the first thing we do is we atomize it from a molecule to an atom. And we are going to get two atoms of fluorine. We are getting two atoms of fluorine because up here we are having two fluorine atoms. So after atomizing it, we put these two here to ensure that we remain with the balance that is present in the equation. We will remain with two atoms of fluorine. But after having these two atoms of fluorine, remember that the energy that was given was only for one atom of fluorine atom. So that's why we get that energy, and then we multiply it by the 2, or the coefficient which is present here down. And you're going to do the same when it comes to its first electron affinity. When you find the first electron affinity of fluorine, we get a negatively charged fluoride ion. And you put here 2 because the 2 we retain the 2 so that we keep the equations balanced with constant number of atoms of fluorine. So you shall put here 2, and once you put here 2 as a coefficient, you have also to multiply it with its energy value, because always the energy values that are given are for one fluoride ion, not 2. So in our solution you're having 2 fluoride ions. So that's why we are multiplying the energy terms by the coefficients present on our terms. And as you're writing your energy, you make sure that if you haven't sub-prescribed it using the denotions or denotient symbols, you make sure that you give the energy its SI units, kilojoules per mole, and K is a small letter, J is capital, and others are all small letters. -1 is a superscript. So formation of calcium fluoride, we say that lattice energy, formation of anionic crystal lattice from its gaseous ends is what we term as lattice energy, which is denoted by this symbol. Or someone may write the L in full by saying delta H lattice in subscript format. So formation of calcium fluoride from its respective gaseous ends is what is going to give us lattice energy of calcium fluoride, which is required by the question. So for us to get this, we are going to use Hess's law. Now remember that Hess's law says that enthalpy change for this overall reaction, which was up here, is going to be equal to summation of all the forces that are involved in the different steps. So you're going to be using Hess's law in mastery of this concept. So you are going to note that according to Hess's law, the overall energy change in the process is going to depend only on the energy of the initial and then the final steps, and not on the routes that are being taken. Thus, the enthalpy of formation of calcium fluoride is going to be equal to the summation of all the energy terms that are going on in various steps, just like I earlier explained. So you're going to apply Hess's law and you're going to say that enthalpy change for the overall formation of calcium fluoride, which was given as -1214, is going to be equal to the summation of the overall enthalpies that are involved in getting calcium fluoride. So that's going to be all the summation of the energies that you saw on our energy level diagrams as we got them. And then what you make, we sum them up and then you make delta HL, which is the lattice energy of formation of calcium fluoride, the subject. So making it the subject, we shall have -2609 kilojoules per mole. I told you that kilojoules per mole, K is a small letter, J is capital, and others are small letters. -1 is a superscript. So let's look at question 2 to master the concept properly. So in this concept, we are given the following thermochemical data. We are given atomization of chlorine to be positive 122. Atomization of barium is going to be positive 178. The first ionization energy of barium is going to be positive 502. And second ionization energy of barium is going to be positive 966. Now the lattice energy for formation of barium chloride is going to be negative 2069. And then the enthalpy of formation of barium chloride is going to be negative 860 kilojoules per mole. So let's look at the energy level diagram, or let's look at the questions that are involved in that. So starting, all the prompted questions are going to be, Roman number 1, you're going to be constructing a Born-Haber cycle for the formation of barium chloride. And Roman number 2, we are going to be calculating for the electron affinity of the chlorine atom. So let's start with the solution for Roman number 1. So first of all, we write a well-balanced equation. That's the first step. Well-balanced equation together with the enthalpy or the standard enthalpy of formation of barium chloride on top of the arrow, which was given as negative 860 kilojoules per mole. After that, we ensure that all the elements are present in their standard states or in their normal states. Barium, its normal state is solid. Chlorine, its normal state is gas. And then barium chloride, its normal state is solid. States are very crucial in thermochemistry because it's one of the reasons why majority of the students are marked wrong. Improper presentation of the states and presentation of the starting to write the terms, these energy terms, without balancing the equation. So after ensuring that all the elements are in their proper standard states, we ensure that the equation is well balanced. And if you look at the reactant side and the product side, all the atoms are well balanced. And then we start to refer to our question about the energy terms that were given. So I told that atomization of barium or sublimation of barium was given as positive 178 kilojoules per mole. Then we go to the ionization energies. Ionization of first ionization energy was given as positive 502 kilojoules per mole. And then the second ionization energy was given as positive 966 kilojoules per mole to give us the barium ion, which is denoted by this symbol. Make sure that all you're dealing with gaseous ions. we deal with gaseous ends and gaseous ends. Gaseous atoms, from an element, we go to a gaseous atom. From a gaseous atom, we go to a gaseous end, so that we can get Lattice energy, because for Lattice energy to be attained, we must react gaseous ends. So we start on chlorine, so we remove chlorine from a molecule to its atom. And then we are going to multiply the atom by 2, because we are having 2 atoms in the chlorine molecule. That's why I put here 2. And then we get the energy term that was given in the question. We also multiply it by 2, simply because we are having a 2 as a coefficient on the chlorine atom here. And the energy which was given was only for one chlorine atom. So that's why we multiply it by 2, because we are having 2 chlorine atoms in our energy level diagram, or in our Born-Haber cycle. So to come from the chlorine gas or from a non-metal, we add an electron to it so that you can get the chloride ion, and that is called electron affinity. So electron affinity of chlorine here was not given. So we write its symbol, but remember that you're having a 2 attached to a chlorine. So after getting that, that means that you're going to have 2 chloride ions. And then since you're having 2 chloride ions, that means that you're going to get electron affinities for 2 ions. That's why we are putting here 2 here, simply because these 2 existed down here on the coefficient of the chloride ion in the equation. Then reacting these 2 ions, these 2 gaseous ions in their standard states, is going to give us what we call the lattice energy, which was given as negative 2069 kilojoules per mole. So the question, or Roman number 2, is prompting us to find the lattice energy, or the electron affinity, of the chlorine atom, because it's the only thing that is unknown in our diagram. And by S.'s law, we can easily determine that simply by saying, let's say that the overall enthalpy change for the overall reaction, which is present as negative 860 kilojoules per mole, is equal to the summation of all these small enthalpies that are involved in this equation, or in the determinant step roots. So let's look at that in the next step. So we are going to come and say that using S.'s law, just like I've explained, enthalpy change for the overall reaction is equal to the summation of all the enthalpies that are involved in that equation. So we come and substitute for each of them. Now here I didn't include the signs that are present on these symbols, but make sure that you include the signs always. Whenever you're dealing with summation of energies, include the signs of the energy terms always. So we include them and we substitute for everything. Now putting everything in the calculator, you make 2EA the subject, and after you divide through by this 2, which is the coefficient of electron affinity, you are going to end up with your final answer to be negative 340.5 kilojoules per mole. Now you are supposed to show about 2 more steps between here, showing the simplification of that. I just skipped that due to the space that was available. So let's look at number 3. Number 3, you're going to follow the same terms. Now here, you are provided with the following thermochemical data. Now you are being given standard enthalpies together with their energy terms, which are measured in kilojoules per mole. So bond dissociation energy for oxygen. Now remember that on the energy level diagram, we don't require bond dissociation energy. We only require atomization energy, and we say that atomization energy is half the bond dissociation energy. So you have to be very alert whenever you're given this term here. Atomization energy is half the bond dissociation energy. So that means that if you want to get atomization energy of oxygen, we simply have this value. So bond dissociation energy of oxygen is going to be positive 498, and then atomization energy of barium is going to be positive 178. First ionization energy of barium was given as positive 502, and second ionization energy of barium was given as positive 966. Enthalpy of formation of barium oxide is negative 558, and first electron affinity of oxygen is given as negative 141. Now the second electron affinity of oxygen was given as positive 753. So the questions are going to be to construct a Born-Haber cycle for the formation of barium oxide. And part B, we are going to calculate for the lattice energy of barium oxide. Now here, I provided with you the answer. That means that I didn't draw this myself. So you are required to follow all these steps, just like I've guided you. This is the only way you may have an issue. I've told you, whenever you're having bond dissociation energy, you always have it to get atomization energy. And then be conscious about the states of your reactants and products together with the balancing. You only start distributing this energy if at all your equation is properly balanced. So calculate, and you must end up with this value or with this answer as your final value. In case you find any problem, try to discuss with your friends, or try to consult any of your teachers, or review the previous two examples that I've done for you to see that you properly master the technique. So take the question and try it out on yourself. So looking at the more examples, I've provided more questions for you to try out so that the concept is properly grasped. So make sure that you draw the cycles. Now notice that for the previous examples, we have been drawing Born-Haber cycles. Once you are prompted to draw an energy level diagram, it's going to be different, and we are going to look at such cases. Energy level diagrams involve levels. So energy level diagrams are different from Born-Haber cycles. For cycles, there are the examples that we have been looking at when you're drawing Born-Haber cycles. For energy level diagrams, we draw graphs showing different energies at which specific reactions exist. So we are going to be proceeding by taking these questions down. As you're taking these questions down, you make sure that you practice them with the cycles that you have been doing. I've done two examples for you, so you make sure that you do this by yourself. Try to compare the answers that I've given you with the answers that you're getting. And in case you get it wrong, try to consult a friend or to discuss the number with the friend first. And try to look at the examples that I've given you to see whether you went wrong, or to see whether whether you didn't first balance the equation, or you didn't try to look through your work and mark yourself, because all states must be properly presented. So you also you do these 3 trials and you take them to your teacher for analysis and for guidance. You try to discuss with your friends so that you can get the concept properly. Now let's go to the next heading. Now we have been dealing with Born-Haber cycles. So in this example, we are going to be dealing with energy level diagrams, and we are going to give about 2 examples to let this one sink. But notice that energy level diagrams are the same as Born-Haber cycles. We follow the same paths. But here, energy level diagrams are restricted in that you only handle one element per time. Per level, you only deal with one element. You don't handle them simultaneously like it was in Born-Haber cycles. So you're going to be saying that here, an energy level diagram can be used to break down the steps that are involved in formation of an ionic compound. And the diagram is going to illustrate the energy levels of a substance that are provided in a given reaction. And here, to indicate positive enthalpies, arrows must be pointing upwards. I repeat, to indicate positive enthalpies or energies that have positive values, like these ones, their arrows must be going or pointing upwards on the energy level diagram on each and every level. And then, for those ones that are negative, or those ones that contain negative enthalpies, their arrows must be pointing downwards. And therefore, the steps or the enthalpy changes are similar to the one of the Born-Haber cycles. So let's look at the examples to elaborate that in practically, from theoretical to practical. So we are given the following thermochemical data, and the following thermochemical data, remember that it's going to be the same as the example that we did earlier on, but it's just that this example we did it using Born-Haber cycle, so we are going to do it using energy level diagram. So atomization energy of calcium is going to remain the same, positive 193 kJ per mole. Atomization energy for fluorine is going to remain the same as positive 700 or positive 79 kJ per mole. And the electron affinity for fluorine atom is going to remain negative 348 kJ per mole. Enthalpy of formation of calcium fluoride is going to remain 1214 kJ per mole. And enthalpy of atomization of calcium is going to remain, ionization of calcium is going to remain positive 590. And second ionization energy of calcium is going to remain positive 1150 kilojoules per mole. Now here you are going to be provided with one example to show you that they are the same, but specifically what is going to need to change is that you are only handling one element or one substance per unit level. And also, for arrows going upwards, that means that the enthalpy we are having is positive. For those ones going downwards, that means that the enthalpy we are having is going to be negative. So enthalpy of formations, we start from 0. So this is going to be a 0 level. So this is where we start from. And we first write enthalpy of formation. Now enthalpy of formation, since it's negative, the arrow goes down. And it goes down to the energy level where we write the compound that we are forming. So here we are forming calcium fluoride as in its solid state. So we write it down. So after here, we are going to be handling one atom or one element per time. So we're going to start with calcium. So we convert calcium from a solid to a gaseous atom. And this is going to be a type of sublimation or atomization of calcium. We leave fluorine constant because in energy level diagrams, we only handle one element per time. So right here, its energy value together with the arrow going upwards to show that enthalpy is positive. Together with the ionization energy of calcium, first ionization energy, we take the arrow up to show that enthalpy is positive. We also give the enthalpy its SI units, kilojoules per mole, until we go to the second ionization energy. Now the second ionization energy are the only energy terms that are involved on calcium, and which was positive 1150 kilojoules per mole. So we first leave them at this level because calcium is done, and then we start on the other element, which is going to be fluorine. Now the difference between the energy level diagram and the Born-Haber cycle is that under the energy level diagram, we handle one element per time. But in the Born-Haber cycles, we are seeing that we could handle two elements simultaneously. So the energy level diagram is strictly for one element per time until you reach where it's supposed to reach to, and then you start the other. So first of all, atomization energy of the fluorine molecule is positive, so that's why the arrow is going upwards to give us calcium ion plus two fluorine gas atoms. But notice that you are multiplying the energy of the fluorine because you're having of atomization energy of fluorine by 2 because you're having a 2 as a coefficient on the fluorine atom, because positive 79 kilojoules per mole is the energy for only one atom of fluorine. So since we're having two atoms, we have to multiply the energy by 2 or by the coefficient to get the required energy. Now here, this fluorine atom undergoes what we call electron affinity, and first electron affinity gives off energy or is negative. Now since it's negative, we represent that by an arrow going downwards, and that is going to give us 2 into negative 348 kilojoules per mole, and you're going to end up with this equation. So reacting these gaseous ions is going to give us an energy which is going to be called Lattice energy or delta H lattice, which is going to go straight away to the product that is being formed of calcium fluoride, and they must be at the same level together with this arrow. So the arrow going downwards from the ions must be together at the same level with the arrow that is coming from enthalpy of reaction of calcium solid and fluorine as an element or as a molecule. So let's look at the questions and how we can answer them provided we have made our energy level diagram. Now you can try out these energy level diagrams on the exercises that you tried out. You remove them from Born-Haber cycles into energy level diagrams. So questions involved under there. Part A, we are going to construct an energy level diagram, which you have already done in the previous slide. And then part B, we are going to be using the energy level diagram, and we apply E.t.c's law to calculate for the lattice energy, which is the main emphasis of energy level diagrams. So we calculate for the lattice energy of calcium fluoride. So we simply apply E.t.c's law, and we are going to say that enthalpy for the overall formation of calcium fluoride is going to be equal to the summation of all the enthalpies that have been involved in our energy level diagram. And we make enthalpy of lattice or lattice energy the subject, and we are going to get the same answer like we got from the Born-Haber cycle, which is negative 2609 kilojoules per mole. So you're going to have this as your assignment. So number 1, you have given the following data about formation of rubidium chloride. So you are going to construct an energy level diagram, and then you are going to use your energy level diagram to determine the latest energy of rubidium chloride. And the answer that you must get is negative 692 kilojoules per mole. Make sure that you review my previous example to let this lesson sink, and then you try out this on your own. I say that for you to be good at thermochemistry, you must do a lot of practice and a lot of numbers under thermochemistry so that you can be good at it. So take the notes, pause the video, take the number, and try it out on your own. Make sure that you have the same answer like mine. Now question 2 is going to be our practice question, so make sure that you also take it down. You are provided with a well-balanced equation, and this is a UNEB number. So you are required to draw an energy level diagram, not a Born-Haber cycle, an energy level diagram. However, if you want practice, you can do Born-Haber cycle as a side work if at all you understood that best. And then after or later, try to draw the energy level diagram containing all these energy values and try to put them to practice so that you can master the skill of drawing the energy level diagrams. Like I earlier said, make sure that you get this before getting to the next video. Now the next video is going to be finalizing thermochemistry, and make sure that any areas or concerns that you're having about any particular video are presented to the people who are either greater than you, or to your teachers, or to your classmates that are better than you, who are having more knowledge about the topic compared to you. Or try to replay the video slowly and you understand which areas are specifically highlighted for you to focus on the most. Try to reach me out, try to engage in discussions, and try to be consistent in your revision. Make sure that you subscribe and understand each and every video that I upload on this channel if you want to excel highly. So we're going to draw the energy level diagram for the formation of aluminium oxide. You also calculate from the energy level diagram, you calculate the latest energy of aluminium oxide. Together you comment on the value of the latest energy obtained. Commenting, we talked about this in the first video. It depends on the sign of the value that you have got. This brings us to the end of this video. Your advice: share the video to your friends, subscribe to the channel, and for those of you having papers in examinations success in your papers, so like the video and post it to your friends so that it can be accessed by a large number of people. So see you in the next video.